able to see the OneNote page, guys?
Yes, sir.
Okay. So we are finished with the first unit, that is the internals of the operational amplifier. There are some things which are given in the syllabus, specifically pinouts and all those kinds of very simple things which I would like to cover in some sort of assignments. Okay, like you have to download the data sheet of operational amplifier, a typical operational amplifier, and then go through the various different details over there. Today we are going to start with the actual operational amplifier circuits. But before that, I would like to introduce something called as Miller's theorem. I know you have not done this, so let us have a look at what exactly is Miller's theorem. Okay, so here we go. So for example, if you have a voltage amplifier with a gain equal to A, if you have, this is the input terminal, this is the output terminal, and we have seen such a kind of uh, model. Most of the time this will be ground. Okay, this is node number 1, this is node number 2. Here you have V1, which is the input voltage. Here you have V2, which is the output voltage. Okay, and then we have an impedance connected between the input and the output. We'll call it as Z. Okay. And the current flowing through this Z, we are going to call as I1. Now, many times in operational amplifier, this basically is a typical example of a feedback loop, and many times such a kind of circuit will be used for the operational amplifier based circuits. And our task is to resolve this Z on the input side and the output side, because it becomes otherwise very difficult to find out the transfer function. Okay, so as I said, this shows a voltage amplifier. And impedance Z connected between the input and the output. So at any frequency, the voltage gain between nodes 1 and 2, we can calculate, we can define it as V1 by V2 by V1 is equal to A. Okay. Now generally, A, that is the frequency gain, voltage gain is frequency dependent. Please note this. So now we show that the current I1 drawn from node number 1 through Z can be obtained by disconnecting Z from node 1 and by bridging an impedance Z by 1 minus A from node 1 to ground. This is an important step. So I1 is V1 minus V2 divided by Z. This should be simple. Okay, what is I1? I1 is nothing but whatever is the potential difference between these 2 points, 1 and 2, divided by the input, divided by the impedance Z. This should be easy. That is equal to V1 minus A times V2. Sorry, A times V1 divided by Z, which we can easily see as 1 minus A divided by Z, which actually is equal to V1 by Z1. Okay, so if I club this together, this will be another impedance Z1, where Z1 is Z divided by 1 minus A. Okay, so what we are doing is we are replacing this Z. Okay, at the input side, I am trying to transfer this Z to input side, and that particular value will be Z1, which is equal to Z divided by 1 minus A. This is very, very important. Similarly, node 2 is I2, which is equal to V2 minus V1 by Z. In a similar way, I can write this as V2 by A. For V1, I'm going to write V2 by A divided by Z, which is V2 divided by Z2. Now, what is this Z2? Rather, I should not skip the step. Let me complete that step. What will it be? If I take V2 common, 1 minus 1 by A divided by Z. So, similar manner, I can write this as V2 by Z2, where again Z2 is the impedance between node 2 and ground. So, Z2 happens to be A into Z divided by A minus 1 if you simplify this. Or also we can write it as Z divided by 1 minus 1 by A. Simple form. So Miller's theorem says that if the network has voltage gain of A between two nodes, then any impedance connected between these two nodes can be replaced by an impedance at each node connected to ground. So our circuit, this particular circuit, can be replaced by the circuit which I am going to draw. This is node 1, this is node 2, this is the gain, this is our common ground. So I can replace that Z with an impedance both at input side and output side. Okay. So this is Z1 and this is Z2. Where Z1 is, we have seen, Z divided by 1 minus A, and Z2 is equal to Z divided by 1 minus 1 by A. This is the gist of the theorem. Okay. So it gives you a very nice way of resolving the impedance connected between input and output. You can break it down into impedance which is connected at input and impedance which is connected at the output. This is going to be a very, very useful theorem. Okay. So please remember this theorem quite well. Is the theorem clear to all of you? Guys?
Yes, sir.
Very simple.
Yes, sir.
But please remember, these theorems are not to be forgotten. Just like KVL, KCL, Ohm's law, superposition theorem, we are going to see something about that later. Maximum power transfer theorem, Thevenin theorem, Norton theorem, and this is one addition to that, which is the Miller's theorem. Okay? Now, once we know how to resolve this, we can solve many such problems which involves an impedance which is connected between input and output. Okay. Now I shift to the core of unit number 2. Okay. So I'm not going to write there unit number 2 because I don't think that there should be any discontinuity there. Okay. So we'll start with op-amp. Now that we know the internals, op-amp circuit and its characteristics. Now the next few lectures are going to be very, very important. If you miss those lectures, you're not going to understand operational amplifier at all. Okay, so let us first start with the schematic symbol. So the operational amplifier generally is shown like this, with two inputs, one output. Output is marked as output voltage VO. This is marked as minus, this is marked as plus. The gain, open loop gain, is shown like this as A. Okay, so this will be your V2, this will be your V1. This terminal is called as the inverting terminal.
Sir? Sir?
Yes.
Sir, it is not visible what you are drawing.
Is it? So far it was visible. The Miller's theorem
Visible.
everybody saw.
No, sir, it is visible.
So probably you may be having some problem at your end. Please check. So all the other students are able to see this?
Yes, sir. Yes, sir.
Okay, fine. So this is the inverting terminal, called as the inverting terminal. This will be the non-inverting terminal. In short, we'll always call this as INV and this as non-inverting NI. Here, V1 is the voltage at non-inverting input. V2 is voltage at inverting input. VO is output voltage. A, very important, is called as a large signal voltage gain, which is actually specified in the data sheets. We are actually going to see one data sheet later, which is also called as an open loop gain. Okay, so also called as open loop gain. Now, with the previous lectures that we have seen, in the previous lectures that we have seen, we have already seen what is the significance. I mean, how did this inverting terminal is marked, how non-inverting terminal looks like. I mean, why it is called as non-inverting, why this is called as inverting. We already have seen with the internals of the operational amplifier, right? And then we have also said that there is going to be a large signal, a large voltage gain, open loop voltage gain, which is by design designed to be a very high value. Okay, so this should not be very difficult to understand. Let us see the equivalent circuit of op-amp. But for that, you have to understand some very important parameters of operational amplifier. So the equivalent, we start with the equivalent circuit. So I can draw the equivalent circuit like this. See carefully. So actually the equivalent circuit looks like is shown like this. D2, D1. Mute your microphones, please. Mute your microphones, please. This is the differential input. This is called as the input impedance or input resistance. Okay. This is called as the output resistance. And this is A into VID. And of course, we generally show plus VCC here, and we show in a similar way minus VEE here. So this is called as the equivalent circuit of operational amplifier. Output voltage VO is equal to A into VID. It is much more simpler than the transistor equivalent, as you can see very easily here. So what do you see from here? The equivalent circuit, that between the inverting and the non-inverting inputs, we have a very high resistance Ri. Okay. Output, we have the gain factor which is a voltage source, which is a voltage dependent voltage source, and that is the reason why we have A, that is A times, it is A times VID. Whatever is the differential voltage between these two inputs is amplified by A, where A is the open circuit voltage gain or the large signal gain of the operational amplifier, and then naturally it is shown as a voltage source. Obviously, a non-ideal voltage source will have output resistance also with it. Okay, just like any voltage source, we show like this, no? So this will be the R4. Okay. So is this schematic, is this equivalent circuit of operational amplifier clear to all of you, guys?
Yes, sir.
Yes, sir.
If there is any doubt, please don't be shy and ask the doubts immediately, because this is going to be the foundation of your entire analog design or analog circuitry involving operational amplifier. As I said, operational amplifier is the basic building block of many circuits. So it is very important that you understand the operational amplifier in details, and that is the reason why the internals of the operational amplifier, we took about 11 lectures to cover that. Okay. For those who will be looking out for gate examination and all that, this material is going to be very helpful. Of course, because of time limitations, we have not gone into the details of the current sources, different types of current sources also, which is specifically required for gate examination. In fact, nothing of this is mentioned in your syllabus, but I have taken it so as to have the to get the completeness of the subject. I've been repeating this again and again. Okay, then let us see the characteristics of an ideal op-amp. Okay, I'm going to list down the characteristics. Of course, the electrical characteristics. Please note, I'm talking about ideal op-amp. So for ideal op-amp, what should be the value of A? This one. Ideal. Remember always that whenever somebody tells you, asks you a question related and with the keyword ideal, it either means 0 or infinity. The answer generally is 0 or infinity. Okay. So in case of ideal voltage gain, so what should be the voltage gain?
1.
1. अरे अभी तो बोला ना मैंने, आइडियल कीवर्ड आ गया तो इसका मतलब है उसके दो आंसर्स हो सकते हैं, 0 या फिर इंफिनिटी. और ये 1 कहां से आ गया? Guys, what should be the ideal voltage gain?
0 and infinity.
Yes,
0 and infinity.
both.
Sir, infinity.
क्या बात कर रहे हैं? Come on, this is something ridiculous. So it should have infinite voltage gain. A. Don't get confused. I said whenever somebody asks you a question related to ideal parameter or characteristics, the possible answers can be either 0 or infinity, not both, obviously. How can it be both? So you have to think carefully. This is a very typical question. Okay, what about the input impedance? Ideal input for ideal operational amplifier, what should be the input impedance?
Infinite.
Infinite. Now that is correct. So infinite input resistance Ri. So Ri should be infinite. Why should it be infinite?
Sir, to prevent attenuation.
What is the specific word?
Loading effect.
Excellent. So there should be so that there is no loading on the previous stage. Or source. You should justify also. Okay. What about output impedance or output resistance? RO?
Zero.
Zero.
Excellent. Zero output resistance. And what is the justification for that again? Yes? What is the justification for this, guys?
Loading effect only.
Yes? So that it is not loaded by the next stage or load. Again, loading effect. Concept of loading effect. This is going to be ubiquitous. Understood?
Yes, sir.
What about bandwidth? What should be the bandwidth? Ideal bandwidth, ideal operational amplifier bandwidth.
Infinite.
Yes? Infinite bandwidth. It means that our amplifier can work with a frequency right from 0 hertz to infinite hertz without guys.
Yes, sir.
What is 0 hertz?
Frequency 0.
Means what? It is DC. 0 hertz means DC. So our operational amplifier should amplify right from DC signal to a frequency of infinite value. Okay? Is that clear? Okay, now we know what is common mode rejection ratio, CMRR. We have seen this with respect to differential amplifier, and we have this for operational amplifier as well, obviously, because differential amplifier is the building block of operational amplifier. So this is a very important factor for operational amplifier. So what should be the value of CMRR? Ideal op amp, what should be the CMRR?
Sir, infinite.
Infinite. So infinite CMRR. So that what? Common mode signal, which is mostly noise, is completely attenuated. All right. Number 6. Okay. So if both the voltages are equal, that is when V1 is equal to V2, what should be the output? V1 or VID is V1 minus V2, and output is A into VID. So when V1 is equal to V2, what is the value of VID? What is the value of VID?
Zero.
0. So what should be the output voltage?
Zero.
So 0.
This may look trivial, but we will see that why it is practically it is not so. So 0 VO when VID is equal to 0. You can call this as a perfect balance. All right.
I like the file.
Okay. So 0 output when differential voltage is 0. Okay. Next. Now there is something called as slew rate. We are going to talk in more details about this. But for the time being, it should be infinite slew rate. And last, all the characteristics do not drift with temperature. So this is what our ideal operational amplifier would look like with these electrical characteristics. Okay. Have you understood this? Except for the slew rate, which we haven't discussed as yet. We are going to discuss it immediately. So have you understood these, at least the 7 characteristics of the ideal operational amplifier, guys? Hello?
Yes, sir.
Yes, sir.
It's not at all difficult to understand.
Yes, sir.
Okay, now what we do is I'll say something about what is a slew rate. It is defined as it is the time rate of change of the closed loop amplifier output voltage under large signal conditions. Now I'll repeat here what is large signal. What do you mean by large signal? If the signal goes in, let us say, in volts, we normally call it as a large signal. Okay. So if the output voltage is like 1 volt and above, maybe even more than that, in that case we call it as a large signal. Whereas if the signal is in the millivolt, microvolt range, we call it as a small signal. Okay, simple. Have you understood the difference between large signal and small signal? That is to be understood first. Okay, guys. Hello.
Yes, sir.
Okay, so I can write mathematically the slew rate equation or definition as maximum change in output voltage divided by, since it is time related, time rate, change in time. So I can put it down in notation. Delta V out maximum divided by delta T. In terms of calculus, since it is a rate, we can write it as d d by dt of VO max. And what will be the units for this slew rate? What will be the unit?
Volts per second.
Volts per second, but generally it is given as volts per microseconds. Remember this. Okay. So in plain words, slew rate indicates how rapidly the output of op-amp can change in response to changes in the input. For that, if I take an amplifier, now this is in a square wave. What is the rate of change at the transitions? Guys, what is the rate of change?
Infinity.
Infinity. Very good. Now your operational amplifier or any amplifier, as a matter of fact, will not be a perfect amplifier or an ideal amplifier. So it is not capable of reproducing the same kind of output. And in other words, you'll get something like this. Do you see the difference? Do you see the difference?
Yes, sir.
So this rate of output change with time is actually the characteristics of this amplifier. So higher the rate, slew rate, that is, this is nothing but the slew rate. Higher the slew rate, better will be the operational amplifier, isn't it? Guys?
Yes, sir.
So this figure actually describes the effect of low slew rate of amplifier on the output signal. So this is not having a good slew rate, high slew rate. It is having a low slew rate. So if you have another amplifier and if you see that the output is now, well, not really exactly like this, but maybe slightly like this, then you can say that, okay, I find this seems to be a better slew rate operation, a better slew rate amplifier. So slew rate is a very, very important, one of the most important parameters for operational amplifier. So I can say slew rate is a figure of merit. Okay, and it actually is a very important selection criteria. So whenever you see an operational amplifier, it will have its own slew rate by design. Generally, slew rate is specified at unity gain by the manufacturer. ठीक है? Okay with this, guys? Guys, okay? Are you okay with this?
Yes, sir.
Yes, sir.
All right. We'll see more about slew rate because slew rate is going to be a very important criteria. So we are going to see more about that in more in details. Okay. Let us shift our attention to the ideal voltage transfer curve or the transfer function. Okay, for an ideal operational amplifier, what will be the ideal transfer function? We have VO as A into VID, which we already know is A into V1 minus V2. That is fine. Now, if I want to express this graphically, this particular transfer function, if I want to express graphically, what can we do? What can we do? We can plot. So plot VO versus VID, and obviously gain will be constant there. Okay. So how will it look like? Let me draw that. So this is the positive VID. You can have negative VID also. Okay. And then I'll mark something here. And the transfer curve looks like this. So it should be the other way around. Just messed with the scale here. Okay. Let me rectify that. So look at it very carefully. This is a transfer function. Here you have this part is the linear region. Okay. And now This is important. This will be a level. This will also be a level. And this is called as, this level is called as a positive saturation. Okay. Generally, this value is Vsat. It is called as plus Vsat, which is equal to nearly 90% of VCC. Similarly, this level is called as negative saturation, technically voltage, negative saturation voltage, and this is also Vsat minus Vsat is equal to 90% of VEE. Remember, VEE is negative. Look at this transfer curve very carefully. What do you understand from this? Guys, what do you understand from this curve?
So the op-amp should be
Behaves as an amplifier.
or
Op-amp behaves as an amplifier with a constant gain of A, that is actually the slope of this line, linear region, from this point to this point. So whenever the voltage is between VID is between some certain limits, that this limits, so within this limits, VID is within this limits, I'm going to see that the operational amplifier will be working as an amplifier. Output of the operational amplifier will either go to plus Vsat or it will go to minus Vsat. In any case, Vout cannot exceed the saturation values. Saturation voltages. Remember this. Immediately, I would like to ask you a simple question. Say, for example, if you are given a question, a problem, okay? Say I'm having an amplifier. I'm not saying whether it is operational amplifier or what. It is an amplifier. It's a voltage amplifier with a gain of 100. Guys, are you able to see that?
Yes,
Hello?
sir.
And if I provide 1 volt as the input, what will be the output? Tell me.
100
100 volts.
100 volts.
Really? Really? This is a very tricky question. It's not as easy as it sounds. Is it going to be 100 volts? No. It depends on the supply voltage of this amplifier. If the supply voltage, which is generally, let us say, 12 volts or 20 minus 12 plus minus 12 volts, in that case, the output voltage will be always less than these voltages. Or in case of your common emitter amplifier, single stage common emitter amplifier, it depends on your VCC. It will never go to or beyond VCC. Beyond that, we have saturation. Okay. Are you able to understand that? So if somebody puts a question like this, if the supply voltage is 12 volts, okay, I just instead of a bipolar supply, I will say that the supply voltage of this operational amplifier is 12 volts. Okay, and if the gain is 100, input is 1 volt. How can the output voltage be 100? It will saturate to some value which will be less than plus 12 volts. That is called as saturation. Are you able to understand this? Guys, this is a very, very important concept. Hello?
Yes, sir.
Guys, are you there with me?
Yes, sir.
Yes,
sir.
sir.
See, these kinds of concepts are not discussed in any book or on any video, any link. Your friend Google, no, it is not discussed anywhere like that. So, for those who are simply taking it very casually, they are going to miss this important concept. So, please pay attention carefully to whatever I say. All right. So, I can say that these saturation voltages, again with reference to our positive VSAT and negative VSAT, these saturation voltages are specified by an important parameter given in the datasheet by the manufacturer called as the output voltage swing. This is important, a very important parameter. Okay, for given values of supply voltages. Okay, so I think we are nearing the end of the session. So I'll just have a recap of what we have seen today. Have all of you understood up to this point? Guys?
Yes, sir.
Yes, sir.
In fact, if I show you what is going to happen because of what happens at the saturation, we'll see the simulation later on. Okay. But to have a recap of what we have done today, we started our session with what is called as the Miller's theorem. So what is the Miller's theorem? It simply tells you that you can break down this impedance which is connected between the input and the output terminals and replace it with two impedances, one at the input to ground, other between output to ground, and it is simply the input side is given as Z divided by 1 minus A, where A is the gain of the amplifier. Okay, and the output impedance is given as Z divided by 1 minus 1 by A. Please remember this carefully. It is going to be useful to us when we derive the equations for the input impedance and the output impedance of the operational amplifier according to its configurations. Then we said something about operational amplifier circuit, rather the characteristics of the operational amplifier. We started with the schematics involved. Okay, we see that there are distinct markings over there, like the inverting terminal, non-inverting terminal. Non-inverting terminal is marked with a plus sign over here. Inverting terminal is marked with a negative sign, minus sign over here, and the output. And of course, we are going to specify what is called as the large signal voltage gain, which is also called as the open loop voltage gain. Okay. Then we saw the equivalent circuit of operational amplifier. What is that equivalent circuit? It simply tells us the model. It's a model of the operational amplifier. Okay. It simply tells us, it says that there is a an input resistance Ri between the inverting and the non-inverting inputs. Okay. Then we have the voltage dependent voltage source, which is A into VID, which is actually the amplified version of the differential voltage VID. Similarly, it is accompanied by output resistance RO. Very, very simple model. Then we went on to see, of course, it is also required to specify most of the times the plus VCC and the minus VCC, that is the supply pins. For our ideal operational amplifier, we saw a few electrical characteristics, namely, number one, it should have infinite voltage gain, or you can say that ideal operational amplifier has infinite voltage gain. Number two, infinite input resistance Ri. Number three, zero output resistance Ro. Infinite bandwidth, infinite CMRR, perfect balance, that is when differential input voltage is zero, output also is equal to zero. Then we saw that it should have infinite slew rate. And finally, characteristics which do not drift with temperature. Please remember, this is a semiconductor device ultimately, or composed of semiconductor devices, and so it is going to be temperature sensitive. So ideal operational amplifier would not exhibit the characteristics of drifting with the temperature. Again, this is ideal, and we are going to see how we drift from how we go from ideal to practical values. Okay. Then I said something about slew rate, which I said that it was the time rate of change of closed loop amplifier output voltage under large signal conditions. Okay, it is simply given as d by dt of VO, that is a maximum, and the units are generally in volts per microseconds. Okay, we saw that it can reproduce the output. Finally, we saw the ideal voltage transfer curve and came to know of the different things like linear region and the positive and the negative saturation voltages. Please remember that plus and minus Vsat are equal to 90% of VCC or VEE respectively. Okay? So is that fine with all of you guys?
Yes, sir.
Yes, sir.
So with that,
Yes,
we'll
sir.
here for today. We'll continue tomorrow with more interesting stuff. Okay? So I'm going to
Okay, sir.
stop this meeting.